Hello everyone, this is Joe here with Joe Talks, and today we are going to take a look at the rear suspension of a dirt late model. And specifically, we are going to do a position analysis of that rear suspension. Now, you may have seen some of my previous videos where we did a position analysis on the front suspension, so on a double wishbone front suspension. And we are going to do that same kind of process, but do it for the rear suspension. So looking back on that front suspension, you might remember that front suspension, we could define all of the positions of all the components in that front suspension with two known inputs. And so those inputs were the front inner tie rod, so the steering input, and then also the shock heim to heim, or the shock from the coilover assembly, the center of the heim to the upper to the center of the lower heim, so the shock distance. And so that was a pretty simple process that we went through. Really, if you think about it, if you were to hold the steering input constant, really we could define everything in that suspension simply by knowing the heim to heim distance of that shock. And so we talked a little bit about why there was value in doing this. Specifically, if you're using a data acquisition system for testing, you can set linear pots up on your data acquisition and measure that heim to heim distance, relatively simple. But if all you have is heim to heim distance, that DAC data doesn't really show you a whole lot about what's going on with your suspension. So you really need a math model to be able to take those heim to heim distances and plug into to get all of the other parameters of what your suspension is doing. And so that's what we really are trying to accomplish here. So up to this point with the previous two videos, we've got both of the front left and right suspension, and we did that using two different methods, one using a trilateration process and one using some numerical methods, so just two different approaches. And in this rear suspension, we are going to use the numerical methods. And so one other thing that is different about the rear suspension is that we have not just one shock, but we have three shocks to work with. So we have the shock on the right rear, the shock on the left rear, and for right now we're ignoring the traction shock. However, you could include that into this calculation, but just for simplicity purposes, we're leaving it out. And then you also have the fifth arm shock. And so we are going to be able to fully define the position of this rear axle assembly knowing only the links of those three coilover shocks. Okay, so before we get too far into this video, I'd like to take a few minutes and just for the people who are kind of unfamiliar with what a dirt late model rear suspension looks like and how it works, I want to kind of walk through that, take a few moments. Obviously, if you're watching this, you may already know the inner workings of a rear dirt late model suspension. So if you do, just fast forward to the next section of this video. But I just want to bring everybody up to speed because there may be some people that really haven't ever looked under a dirt late model before. So, but before I get too far ahead, as with any of these videos, please, if you like it or if this helps you at all, please help me out, subscribe, like, all that good stuff. Trying to grow my subscriber count just like everybody else is. So please help me out and subscribe. So let's take a few minutes. What I'm going to show here is a picture of the left rear of a dirt late model. And I stole this off the internet, so if this is your car, I'm sorry. And if you want me to take the picture off, I will. But this was a random picture I pulled off of Google. So, but anyway, let's take a real quick look at this here. So you'll notice in this photo that there's two 4-bar links. So we refer to the rear suspension as a 4-bar or 4-link rear suspension. And where it gets that name is from the connecting bars that connect the rear end to the chassis. And so if you'll notice in this photo right here, what we're looking at is the left rear suspension. And so we have right here is an upper 4-bar link, and down here you see kind of the front end of the lower 4-bar link. And those two links are part of what we call a 4-bar mechanism. And so there's two other bars in this mechanism, and that is the chassis. So the chassis right here creates a bar out of that 4-bar mechanism. And so you could think of this as the ground, if you thought of the chassis as being the quote-unquote ground for the link system. So you have a link here, the upper link, and then you have on what we call a bird cage, and I'll talk about that in just a second. But that creates the third link, and then the lower bar is the fourth link of that 4-bar mechanism. And so you've got a 4-bar mechanism on both sides of the car. So on the left side and the right side both have one of these. And on this bird cage mechanism, so let me explain what a bird cage is for those of you that may not know. This is a very simple bird cage mechanism. So when we talk about the rear suspension of a dirt late model, we refer to that as being a live action decoupled rear suspension. And so that means that the axle is live. So if you've ever grown up on a farm or been around farms where you've got an old grain truck, for example, and it's got a solid I-beam front suspension, that would be referred to as a dead axle, right? Because it doesn't transfer any power. But when an axle transfers power to the ground, we refer to that as a live axle. And so this is obviously transferring power to the ground in the rear of the race car, so we refer to that as a live suspension. Now we refer to it as a decoupled suspension because these bird cages, or the brackets where the 4-bar links connect to the axle housing, are not rigidly mounted. So if you think of a traditional car like a 4-bar like metric link suspension on like a street stock or something, the brackets where the connecting links connect to the rear end are solidly welded to the housing of that axle. So when we apply power to a live axle, the axle is going to have a tendency to counter rotate with the power that's coming through the engine. So sometimes we refer to that as the pinion climbing the ring gear in the rear axle assembly. So something has to counteract that force, and in a coupled rear suspension, all that axle rotation gets reacted through the links that are solidly welded, or the brackets that are welded onto the housing of the axle. And then the links actually counteract that rotational force. But in a dirt late model, we have what are called bird cages. And in that side of that bird cage where that axle tube goes through, there's a bearing. And this entire housing is free to rotate on that axle tube. And so we call that a decoupled connection point. So that is where we get the term a live action decoupled rear suspension, because the axle housing is decoupled or not rigidly connected to the brackets that the 4-bar links connect to. And so we have to counteract that rotational force with other means, and in most dirt late models we do that with what's called a fifth arm. And so earlier you heard me talk about the fifth arm coil, or that third spring in this rear suspension. So if you look in this picture right here, there's an arm that goes forward from this bell housing on the axle, and that's referred to as the fifth arm. And there's a spring at the end of that arm that goes up and connects to the frame, and that's referred to as our fifth coil spring. And so that is what actually counteracts that reaction rotation of the axle from the engine torque. And so this is the rear suspension. Now, the springs don't directly connect to the axle housing. The springs connect to the bird cages. So if we go back and look at that photo, as you see here, obviously this would be where the axle tube goes through. And then our upper 4-bar links would mount up here. And you see there's some different adjustment points where you can mount that 4-bar link. And then on the lower, just as well, there's some adjustments, but this is where the lower 4-bar link would connect. And then the shock connects to a third point on this bird cage. and then that is where you get the 3 connection points to that birdcage. The upper and lower 4-bar link and the shock that all connect to this assembly. And so this one is pretty simple. They get kind of complex. Here is a example of a, kind of a nicer birdcage assembly that would go on the left rear. But same kind of thing. You've got your lower 4-bar link would connect down here. The upper would connect up here. You got your axle tube. And then on this assembly, there's a spot here where the brake caliper would connect. And then this also has a brake floater arm. We won't talk about that here because that's kind of a little more complicated. But you can see that these kind of can get a little more complicated. But the basic operation, though, is quite simple. It's just a couple of connection points for your 4-bar links, a connecting point for your spring, and a place for the axle tube, and something that allow that frame or that connection point, the birdcage, to rotate on the axle. And so that is a birdcage. Our 4-bar links, our bird cages, our axle assembly, our 5th arm. Oh, and one other thing I forgot to mention is we also have what's called a J-bar. So something in this rear end has to locate the axle laterally. So, in that old metric rear suspension, the upper control arms were at an angle, and those control arms would actually control the lateral position of that assembly. But in this rear end, the 4-bar links are actually more longitudinal with the chassis, and so they don't provide any lateral positioning of the rear end. So we have to have another link to control that position, and we do that using a J-bar link. And so if you look right here, you can kind of see there's a bar, it's hidden by the upper 4-bar link in this picture, but that is it, and it connects at the chassis, and then there's a bracket, usually right next or right around the pinion, that the J-bar will connect to. And so that is what controls the axle laterally. So we have our upper, lower 4-bar links, the axle, the 5th arm, and the J-bar. And so we are going to completely define the position of all of these elements in this rear suspension. And using all of our outputs from our model, we're going to be able to determine things like birdcage indexing, rear steer, 5th arm position, J-bar angle, spring, I don't know if you want to call it spring perch, but spring angle, or spring, how the spring is angled to the chassis. Anything in this rear suspension, you name it, we're going to be able to figure out what it is. So one other thing I do want to point out in this rear suspension. So when we talk about the 5th arm, there are kind of 2 configurations for how we typically use a 5th arm on a rear end. So one of those, and this is what we're going to use in this model, is what, I don't know what the technical term would be, but I call it a gusseted 5th arm. And so that is a 5th arm that is connected to the rear end, and then there's another member that triangulates that rear end so that it stays at a constant angle to the axle tube. And then there is a second style where I kind of refer to it as a floating 5th arm. Again, I'm not sure what the technical name is, but it does not have that gusseted member. And so if you look on those, there's an actual 6th link at the front of the 5th arm that goes laterally and connects to the chassis. And in this configuration, the 5th arm is held more longitudinal with the chassis frame, whereas the rear end can kind of move around, and that angle between the 5th arm and the axle tube will change, whereas with the gusseted configuration, that angle will stay more consistent. And so we are going to do the gusseted method just to kind of keep things simplified, but I think when you'll find at the end of this video, you can extend these methods to include some calculations to do that floating style of 5th arm, if that happens to be what you have on your car. Okay, so now that everyone is clear on what a dirt late model rear suspension is, kind of how it's laid out, let's jump into taking a deeper look at some of these points that we're going to be looking at. and start kind of pre-processing some of the things that we need to look at and get some organization into our model. Okay, so what we're looking at here is a inventor model of our suspension, and it's really kind of a skeleton view of what this suspension is going to be. I've got this broken down into different chassis points and then also the points in that rear suspension that we're going to be interested in looking at. So what we're looking at here is 3 different sections of this model. So throughout this process, I've got this rear suspension broken down into 3 different bodies. And so we are going to be using what's called a multi-body systems approach to solving this or to doing this position analysis. So you can kind of take those old planar calculations that you might have done in school and toss those out the window, because we're not going to be using any of that stuff. This is all going to be the multi-body assembly approach. We're basically going to be replicating some of the processes that like SolidWorks or Inventor would be using in the background. We're just going to basically write our own code to do that same thing. So in this model, I've got it broken down into 3 different sections. I've got the center section of the rear axle assembly, and in that center section we include the 5th arm. And so what you're looking at right here in this wireframe is kind of conceptually the 5th arm, and then this point right down here, and I'm going to dive into these in a little more detail, but basically where the J-bar mounts, where the 5th arm spring mounts. And then I've also got the bird cages broken up into a left side body and a right side body. Now, one thing I want to point out is in these bird cage bodies, you saw in those pictures where that axle tube goes through the bearing assembly. Now, in our mathematical model, even though obviously it isn't like this in the real world, I want you to think about if we were to slice that axle into 3 different sections and have a center section of that axle tube that goes with the center axle housing or the center axle section, and then a section of that axle tube that kind of goes with the left birdcage assembly, and then the other part of that axle tube going with the right birdcage assembly. And so that's going to leave us with 3 bodies: the left birdcage body, the center axle body, and the right birdcage body. And so that's what we're looking at here. We've got the center, we've got the left birdcage assembly, and then the right birdcage assembly. And so let's go in there, and I'll kind of show those in a little more detail. All right, and so one of the first things we're going to want to do is we have to provide some definition to what these points are. So basically that means we need to establish a numbering system and identify each one of those points with some type of numerical value. And so that's what we are doing here. And so one of the first things we have to define, just like we did, if you remember, in that front suspension, if you remember, we're holding the suspension stationary and we're moving the suspension components underneath the stationary chassis. And so that might be counterintuitive to what you're thinking about in the real world, where the axle stays kind of more stationary to the track and the chassis kind of rolls around. But in our math model, we're holding the chassis stationary, and we're kind of considering that our quote-unquote ground of our system. And then everything underneath it is going to move relative to that chassis, that grounded chassis. So just like the front, we had to measure out all those pickup points on the chassis for the front, and we have to do that same thing for the rear. And so we need to know in that 3-dimensional space an X, a Y, and a Z for each of those points. And so I'm not going to go into how to measure out a chassis. We could probably do another whole video on that. But basically, for every point, just kind of remember, we need that X dimension, a Y dimension, and a Z dimension. And so just a reminder, X is longitudinal in the chassis, so positive X to the front, negative X to the rear. And then Y is the lateral position, so positive Y to the left, negative Y to the right. And then the Z position is, and I've kind of done this reverse of the SAE, but basically positive Z in the ground pointing up, negative Z pointing down. And so that is our coordinate system. So when I say give me the three-dimensional points or three-dimensional coordinates of a point, that's what I'm talking about. That X, the Y, and the Z position. And you're going to see that quite a bit here in just a little bit. So, but just a real quick summary of the chassis pickup points that we're talking about here. So we have point 1 would be on the chassis where the upper 4-bar link mounts on the left side. Point 4, and don't mind that these numbers are not in sequential order. That's just kind of the way my numbering system worked out. But it doesn't really matter as long as there's a very clear definition of what that point is. I mean, you could call it anything. But this is just the way my numbering system kind of fell out here. So we've got point 1 being the upper 4-bar link on the left. Point 4 being the lower 4-bar link on the chassis. Point 5 being the upper shock mount. And then on the right side, similarly, point 13 being the upper 4-bar link mount on the chassis, 15 being the lower 4-bar link on the chassis, 17 being the upper shock mount on the chassis, point 8, excuse me, being the J-bar mount on the chassis, and point 10 being the fifth arm spring upper mount on the chassis. And so right now, you know, these are all stationary points on the chassis, but you know, as everybody knows, on a dirt late model, there's all kinds of adjustments. I mean, really, every point that I just described on a dirt late model, you can adjust, right? And so you can imagine, you know, it'd be a lot of work to measure out all the points, but you could map out all of the different adjustments points on your chassis. And ideally, with a model like this, you know, not only could you use it for data acquisition, but you could also use it kind of as a predictive idea to figure out if I change this, what else changes type of thing, right? And so that's always kind of the conundrum in dirt late model racing or any kind of racing. It seems like you make one adjustment, you affect two other things, right? And so having a model like this is going to help you figure out, okay, I made an adjustment here, but what other three things moved on me, right? And what can I change somewhere else in the chassis to compensate for those other things that moved to get it kind of back to where I wanted it to be. And so this is where in your model you could very easily plug in a different three-dimensional point. Say, for example, you wanted to move your upper spring mount. Well, if you knew what the three-dimensional points were for each of those adjustments, you could very easily plug in a new point, rerun your model, see what changed, right? And so that is one benefit of having all these data points and using a model like this. And so, those are the chassis pickup points that we'll have to have measured. Now, let's look at the bird cage. Kind of already talked about a lot of these points, but we'll just go over them briefly. Point 2 is the upper 4-bar link on the bird cage. Point 3 is the lower 4-bar link on the bird cage. Point 6 is the lower shock mount on the bird cage. And then these other 3 points, these are some points that are going to lie on the axis of that little section of axle tube that I mentioned that we're going to put in to this bird cage assembly. And so point 7 is that outer point of that axle. And then what I refer to PN1, that's just another numbering system that I'm using for a point. I'm kind of referring to it as an alignment point. But that is the point on the inside of that axle tube. And then point 21 is the hub face. So basically the center of where the wheel is going to mount on the hub. And the reason I made that a separate point is that sometimes you might put spacers on your center of your hub, and so that gives you just kind of another way to make an adjustment to determine how things might change. And so But those are the points for that bird cage. And now, one other thing I want to point out, and you may remember when we talked about this on the front suspension, is that these points are going to be in a local coordinate system to that bird cage. And so those chassis points we picked up, we're going to refer to that as the ground coordinate system or the chassis coordinate system. And all those points are measured in the chassis coordinate system. But for our bird cage, we want to measure those in a local coordinate system to that bird cage. And so what that means is you can make all these measurements on a bench top somewhere, right? So you could make a little homemade CMM machine, set it up on your bench top, put your bird cage assembly on there, and measure out all these points sitting on a bench somewhere. Part doesn't have to be on the car, right? Or if you can sweet talk your birdcage manufacturer into giving you those dimensions, which is highly unlikely, but if you have a good relationship with them, who knows? They might give you those data points, and you could plug those in as local coordinates in that local coordinate system. And so those are the left side birdcage points. And our axle center point, we have our lower J-bar mount, and so this would be where that J-bar mounts to the bracket of that axle assembly. At point 11 is the lower heim joint of that fifth coil or fifth arm coil spring. And then point 12 and PN2 are basically those points along the axle where we made that break. So on the left side of the car, kind of where did we, hypothetically make that break, and conversely on the right side. And so that's what those 2 points are. And again, those can all be measured in a local coordinate system to that axle assembly. And so you don't need to measure those while the parts are installed on the car. You certainly could, but sometimes it's easier to measure those things out when the parts are not installed on the car. Okay, and so on the right side, almost a mirror image to what we just talked about to the left side. We got the upper 4-bar mount as point 14. Point 16 is the lower 4-bar mount. 18 is the lower shock. 19 is that outer portion of the axle, or the outer center point. PN3 is the inner center point. And then point 22 is, again, that hub face, but for the right side of the car. And so those are all of the points that we have to measure out ahead of time before we ever do any kind of analysis. And so it's a lot of data points to measure, I know. Yeah, I mean, that's just going to be a lot of work to measure that stuff out. But, to the victor go the spoils, and to be a victor, you got to do a lot of work sometimes, and that's just the way it is. So, but if you want to do this kind of analysis, this is a very clear path on what you have to do. Yeah, it's hard, a lot of work, a lot of time, but very little ambiguity, right? You know exactly what it is that you need to do. So, but anyway, these are all the points that have to be measured. And once we know, all those points, we can go plug those into our code and do our analysis. So. Okay, so now that we know what all of our points are, we've given them some definition, and at this point, we're going to make the assumption that we have measured out our chassis and we've measured all those points that we just talked about. Now we can go plug all those values into our code and do our position analysis. So let's go take a look at the code that I've written, and I'm going to kind of step through that and explain everything we're doing. And then once we've done that, we will run it and compare it to our inventor model, just to show that our math matches what inventor is putting out. Okay. Now I am doing all of this in Python, but you could easily do this in like MATLAB or something like that, or probably any type of code that's got some math libraries associated with it. Python is really nice because, well, it's really easy to use. It's free. It's always the best part. But it also has some packages called NumPy and SciPy. and those have some really good kind of built-in libraries, especially when you're doing kind of some intricate math or doing any type of numerical analysis. A lot of that stuff's kind of built right in there, and so that makes it really nice. And so what I've got here is a couple of scripts or lines of code that we're going to use. The first one is called kinematics rear, and so this is kind of a first phase of the program where we do some kind of pre-processing a little bit, and then I've got another one called rear EQs or rear equations, and this is where we build all of the equations that actually do the analysis, and then we return those values back to that original kinematics rear module to actually give us the output. And so let's step through this real quick, and we'll just, it's not very long, it's not too bad. We'll just go through it here. Again, I'm using the NumPy package here, and I've imported this other module that I wrote. And so we've created a def or a function here called kinRear, and the input to this is are 3 shock links, and so those, like I mentioned at the beginning of the video, those are the inputs to our model. And then if you remember back when we did the front suspension, anytime you use numerical methods, you have to give the system a set of initial guesses. And so the way those numerical methods work is they go through an iterative process and they converge on a solution. And so your initial guesses basically give that solution process a starting point. And so they don't have to be dead on. They really don't even have to be that close. They just kind of got to be in the ballpark. And so we kind of figure out what those are, and then we feed those as initial guesses. But again, they don't have to be that accurate. They really don't have to be that close. They just kind of got to be in the ballpark. So those are the inputs, that shock length, and my I guess variable or initial guess. And then this first section right here, all we're doing here is we are initializing arrays, and these are just buckets that we use for repositories for data. And so we have just various arrays, and these are NumPy arrays that we initialize, and we're going to use those later on. But we're getting down here to the meat of it. So right here, we need to define all of those points, and so we need to assign all those measured points to our point variables. And so a couple of those arrays that I defined earlier, one of them is called P for points, and one's called L for links. So P obviously are the pickup points, and in each one of those, I make those a 3-dimensional array. And so the first position in that array, so I'll look at this one here, for example. Position 1 is the point number, so 0.1. The second position in that array is the coordinate, so 0 for x, 1 for y, 2 for z. And then the third position in the array, I'm just defining that at a 0 to be in the chassis coordinate system, or 1 for the local coordinate system. And you'll see why we're going to use that here in just a few minutes. But those are how that P array is broken down. And then the L array is just a single dimension array, but those are what we're assigning the length. So like your 4-bar length, your J-bar length, your shock lengths, those are all of those things we are assigning to that L array. And so as we scroll down through here, those like J-bar links and things, that's another adjustment, right, that we can make. We talked about making chassis pickup point adjustments. Well, link links are also very common adjustments, and so that's another parameter that we can assign to our model. But it's not an input to the model because it's not something that's going to change when we do our analysis, right? Once we set it, it's not going to move until we wanted to make an adjustment. So that's very similar to like your car, right? Your suspension moves all over the place, but once you set a J-bar length, it doesn't move. It is what it is until you make an adjustment. So it's very similar in that aspect to our math model as well. And so it is a parameter, but it's not an input to the function. So we define those parameters here. So this first layer, those are the inputs, and then our shock length. And then these are the chassis pickup points that we talked about defining. So as you can see here, these are the coordinates that I've measured out in my coordinate layout system. So relative to where I've placed my origin is where these points just kind of were measured out at. And now those were in the chassis coordinate system. And then I've got right here, we start doing our bird cage calculation, or not calculations, but we do our bird cage measurements. And so this is where, for example, I'm doing the left side bird cage. Again, you can see those numbers are kind of more in line with what you might expect from a local measurement, right? So my upper bird cage is, 0, 4, and 4.5. That means it's 0 in the X, 4 in the Y, and 4.5 in the Z, right? And so those are just the measurements that I've taken. But as you see, all of these values right here, these are all in that local birdcage coordinate system. And so as you see, that last parameter of the array, I've assigned that a 1 to indicate that those are in the local coordinate system. And then we'll just keep on going. We get into the center section. Again, here, those are those chassis pickup points. So you notice that third parameter is a 0. Come on down here, and then this is where in our local coordinate system where we've kind of defined that axle and fifth arm, the physical links and configuration of that system, or of that part. Again, these are all in that local coordinate system. And then same thing here for the right. So you can kind of see I'm just kind of repeating this pattern of workflow. Define the chassis coordinates, assign our links, and then all of those local coordinates for that right side birdcage. And so that is where we have given definition to those coordinates, pick those points for each of those parts. And so those are kind of manual parameters that we're given this system. And so once we have all those values, there's a lot of different parameters that we're going to measure as far as magnitudes. And so if you remember back in the front suspension, we kind of built the different components using those pickup points. Well, we want to know the magnitude between each of those points, right? And so one of the things, the reason we can measure all those like points in the local coordinate system is because we're going to use those points to calculate angles and magnitudes. And so one concept we talked about in those front suspension videos was the difference between a scalar value and a vector value. So just a quick overview. A vector value has a magnitude and direction, whereas a scalar value only has magnitude. So a vector is going to be relative to whatever coordinate system you're in, because it's going to give you magnitude and direction, but that direction is going to be relative to your whatever frame of reference you're in, or coordinate system you're in. But the magnitudes, if you're only talking about the scalar value, we can transfer those in and out of coordinate systems. And so what we're doing here is we're using those local coordinate systems to calculate magnitudes, and then we're going to take those magnitudes and use those in the chassis coordinate system to recalculate new points, but what those points are in the chassis coordinate system. And we're going to kind of build our assembly, and we're going to one of the outputs from our calculation is going to be what all those new points are, but in the chassis coordinate system. And so that is what we are looking at right here is when I, yeah, and again, feel free to pause the video. None of this is proprietary. Feel free to copy any of this if you want. If you want me to send you copies of this file, I'll be happy to do that if you message me. But just to give you a quick explanation of what this is, so I've tried to use kind of a smart naming system here. So I've got different arrays that I've defined. So this array called VL7_2. So what I'm kind of referring to as a vector length, or that magnitude, right? So vector length from 0.7 to 0.2, right? And so you see that calculation here, and we're breaking this down into the X, the Y, and the Z components. So for each one of these, you know, VL, so on and so forth arrays, they're single dimension with length 3. So we got 0, 1, 2. So 0 being X, 1 being Y, 2. Position, I guess I should make this up. Position 0 of the array is X. Position 1 of the array is Y. And position 2 of the array is Z. Right, and so that's what you see here. And so we are just determining what those deltas are for those vector lengths of those, each one of those dimensions. And we do that for all of the different lengths that we're interested in. And then we come down here and we can determine what the overall vector magnitude is, right? So the VL was just the component lengths, so the X length of the vector, right? So any vector in XYZ coordinate system, any vector has XYZ components, and so we can calculate the X dimension length, the Y dimension length, and the Z dimension length. And that's what we were doing up here. And then we can use those values to calculate the overall vector magnitude. And that's what we're doing here. And we're simply using good old Pythagorean theorem, right? We just plug those values in and we back out what our magnitudes are, right? So vector 7, 2 magnitude, vector 7, 6, right? And so if we were to come back over here and look at our lengths, right, 7, 2 would be the distance between this point and this point. 7, 3 would be the distance between 0.7, 0.3. Magnitude 7, 6 would be the distance between 7 and 0.6, right? And so on and so forth. And we can use those magnitudes as parameters to pass to our system of equations that we're going to use later on. And so, okay, and so we were finding the distance between points. And so that's what a lot of this section right here is what we are doing, is we are just finding the distance between points that we defined in our bodies. And so, and then those magnitudes we're going to pass to our equations module. And now there's also other scenarios where I need to know the angle between vectors, because the same way that a magnitude is a scalar quantity, an angle is a scalar quantity as well. And so we can pass an angle out of one coordinate system into another coordinate system and it still be valid. And so the same way that I'm calculating some magnitudes up here, I'm also calculating some angles. And so right here, we're just using the dot product to back out some angles. I'm not going to go into what the dot product is. You can do your research on that. But dot product, you know, cross product, dot product are some very common mathematical tools when we are working in the 3D space, 3D world. So, but here I've calculated some of those angles. And then what I've done is I've defined another array just called params or parameters. And I'm just starting to populate that array with all of these different magnitudes and angles that I've calculated using those local coordinate points. And so this is, I've done all of that for the left side bird cage. And then similarly, we're just going through a very similar exercise for the center axle section. and assigning those parameters or those values to this parameters array for the center section. And then here we've kind of just done the same thing for the right side, calculating magnitudes between those points, a couple of the angles that I'm interested in having, and then assigning those to that parameters array. And so what we're going to do is we're going to take that parameters array, which contains all of those angles and all of those magnitudes, and then we're going to use those parameters in our system of equations that will ultimately define the position of our rear end. Okay, so we've got our parameters array populated. Right here, I'm just kind of transferring data out of one array into another array. It's kind of not important, really. And so right here is where I am passing all of these values to our secondary module that has the equations where we're going to actually build our system. So this points equal rear EQS, I'm passing that P array, and so that has all of our points. I'm passing that L array, which has all of our links. Passing that params array that we just talked about, and so that is the one that has all of our magnitudes and angles. And then I'm passing this guess array, which has all of our initial guesses. And so all of these values are going to be used in this other module. So let's go take a look at that other module real quick. All right, and so in this module, again, we're using the NumPy library, and we're also using some stuff from that SciPy library. And so up here, I've just imported some of those modules. We're actually using the least squares numerical method to solve for this system of equations that we're going to build. And so that's where I've just imported those. And here I have, this is where I've defined that function. So that rear EQS, you know, this is, that is this right here that I just called. As you can see, those inputs are PL, params, and guess. And then down here, I'm just creating some other arrays that I'm going to use. I've got an input array here. I've actually called Kelly. It's my wife's name, Kelly. So I've used her name as a variable. So, like I was saying, you can call your variables anything you want. So, but so inside of this module or this function, I have a sub function that I've called func for functions. And in here, I have passed this array called X, which is going to be the array that's going to return all of the points that I'm going to define. And then this input array, which I've called Kelly. And so that's just the inputs to this function. And so this first section, I am basically parsing out that params array and reassigning those to some other variables. You probably wouldn't even need to do this. You could probably just use the params array and the address in your calculations, but I like to reassign them to variables that are a little more readable, and so that's kind of what I'm doing here. And then down here is where we are actually starting to build our model. So this is the actual mathematical model that is going to define our system. Okay, and in this math model, we are going to populate that X array. And so everywhere in these equations where you see an array position for X is an unknown value that we're going to define. And so one of the things we need to do is kind of plan out what each of those positions in that X array are going to represent. And so I have an Excel spreadsheet that I put together over here, and in this sheet what you see is this X bracket 0, X bracket 1. Those are the different positions of the array, and what you see here is what each one of those points are going to represent, right? So x0 is going to be the x component for point 2, x1 is going to be the y component for point 2, x2 is going to be the z component of point 2, x3 is going to be the x component, for 6, so on and so forth. So basically each point in that x array represents a x, y, or z component of each of the points that we can consider like unknown points, right? Those are the points that we're trying to figure out, like that we're trying to solve for. And so I like having this in an Excel spreadsheet, kind of use it as a cheat sheet so I can keep everything straight. Because as you can see in these equations right here, it can get kind of messy when all you have to read is the x and the position of that array. So it's nice to have that little cheat sheet, right? But so let's go take a look at what each of this model, right, this system of equations that we're going to solve to define our system. And so let's step through what each of these things are here. Okay, so let's take a look at these equations. And if you were watching really closely, you probably saw some of these scripts change in the video. I actually had some redundant constraints in there that I had commented out earlier, and I just removed those. So you might have seen that shift a little bit, and that's what you were looking at. But basically what we've got here, so if you remember looking at that list earlier, we have 47 unknown values that we're trying to solve for. And so that means that we have to have 47 independent equations to solve for those 47 unknown values. And so that's what we have here. We have a mathematical model consisting of 47 independent equations that we're going to use to solve for those unknowns. And so let's step through some of these, and I will kind of describe what they are. So the first section of this system of equations is a series of equations that we're using to kind of rebuild those bodies, right? So you could think of these as like our rigid body constraints or our rigid body equations. And so these are the equations that we are reconstructing each of those three bodies that we talked about earlier. That left birdcage body, that center axle assembly, and the right birdcage body, right? And so what we are doing here is we're using those magnitudes that we had passed in, and we are again using Pythagorean's theorem, but instead of using our vector component values to calculate the magnitude, we are using the magnitude to figure out what the vector component point values are. And so that's what you see here, right? This is x0 minus x9 squared. You probably recognize here the Pythagorean's theorem. And so one of the other things we've done is we have utilized the dot product. So I also am establishing some position using the angles between those vectors. And when we do that, we use that dot product. And so that's what we're doing right here is we're using the dot product rule. And so anytime you set up these equations, you may not recognize that when we say this equation position equals this equation right here, what we're saying is we're saying that this equation equals 0, right? And so so for each one of these equations, we're making an assumption that it's equal to 0, right? Because originally this would have been for Pythagorean's theorem, it would have been a squared plus b squared plus c squared equals magnitude squared, right? So all we did is we moved the magnitude over to the other side of the equation, and so that means now all of that is equal to 0, right? And so we did the same thing with our dot product. Again, I'm not going to dive into the dot product. You can research that, but if you want to, you can pause the video and you can see how I came up with this equation. But it's another good example of how you don't have to always use the Pythagorean theorem. There's other equations that you can use to bring definition to whatever it is that you're working with. So basically, all of these equations right here are what are being used to, you know, you can almost think of it as physically building that body, but in the mathematical or virtual world, right? And so right here, doing the same thing, building that center axle assembly. And then right here, we are building the right birdcage assembly, right? Right, so at this point in our equations, we have our three bodies defined. But, you know, if you think about it, those bodies are just kind of floating around in space, right? So what's the next thing we need to do? Well, we need to start connecting these bodies to other things. And so we've got our chassis points, right? Because we have those defined. So one of the first things we can do is we can start taking those points and we can say, okay, let's assign some constraints and like connect those to some other things. And so what we can do is come over here and again just use Pythagorean's theorem, but we are going to be using the chassis points, right? Because we have we defined those in our P array because those are known points. We're not trying to solve for those. We already know what those are. So that's why in this equation right here, for example, you see one of the components of the equation is the P, a value out of that P array. And then we assign a length for whatever it is. You know, here we're looking at the left upper 4-bar length. So in equation 28, we are connecting the upper, you know, that point, what was it, point 2, I think it was, whatever. On the bird cage, the upper 4-bar link for the bird cage, we are connecting that to the upper 4-bar connection point on the chassis, right? And so to do that, we're basically saying that the distance between those points have to be equal to whatever the length is, right? And then we do the same thing for the lower 4-bar, you know, do the same thing for the shock, you know, so on and so forth. And so at this point, once we get past equation 35 here, we now have our three bodies. We have our left bird cage that is connected to the chassis via the upper 4-bar link, the lower 4-bar link, and the shock. We have our center body that is connected to the chassis by the J-bar and by the 5th arm shock. And we have the right body that is connected to the chassis with the upper 4-bar link, the lower 4-bar link, and the spring and shock assembly, right? But at this point, those three bodies are just kind of floating around in space, right? They're not connected to anything. We've not defined any constraints that say those things have to be connected, right? And so I'm going to skip a little bit forward a little bit in these equations. You know, one of the things about these constraint equations is they don't have to be in any order. You know, you're solving them simultaneously, so you can, you know, I don't have to build the bodies in the first section of my equation set. I can build that anywhere, but it's just kind of whatever is convenient to you and reads well. But I just happen to have some other constraints down here in equations 42 through 47, and these are some point-to-point constraints, right? And so now we've got these bodies that are floating around, and so what we need to do now is connect those bodies together, right? And so what I'm doing at this point is I'm saying, okay, this is where we're going to take those three axle sections that we had split apart earlier, and we're going to reconnect those, right? And so I'm going to take that PN1 and connect it to that point 12 on the center axle assembly, and then I'm going to take that PN3 and connect it to PN2 on that center axle assembly, and that's what I'm doing here. And so all we're doing right here is we're basically saying, you know, for that PN1 and the 12, make the X components of those points be the same. Make the Y component be the same. Make the Z component be the same. And so what we're basically saying in these constraint equation is that the position of this point and the position of this other point in 3D space need to be equal to each other. They need to be the same, right? So once we get through those points, we now have these three bodies, and they are all connected at those two axle breakpoints that we made, right? But they're still kind of floating around in space, right? There's nothing to keep them, give them any shape, right? They just kind of flop around. And so we need to now go back and develop some constraint equations that say, okay, now take all these axle components that are just floating around in space, and we want to say, okay, put all those and make them all a straight line, right? And we want all of those axle components to lie on the same axis. And so we can do that using a concept called unit vectors. And so a unit vector is a vector that lies on the same path as a major vector, but has a length of 1, but is a collinear and parallel to that line. And we do that by taking the components of that overall vector and dividing it by its magnitude, right? So if I have a vector and it has an x component of x, some x value, I can find the unit vector, the x component of the unit vector, by taking that x value and dividing by the overall vector's magnitude, right? And so that's one of the reasons, we were needing all those magnitudes from our local coordinate system, is you can now kind of see how we're using those in our system of equations to back out all of the values that we need, right? And so that's what we're doing right here in this section, equations 36 through 41. Basically what we're doing is I'm saying, okay, for equation 36, I'm saying take the unit vector that lies along that 0.7 and 0.1 and make it equal to the unit vector of that 0.12 to point PN2. So basically saying that the unit vector that lies along that little axle section of the left bird cage is going to be in the same direction as the unit vector on that center axle section, right? So basically that's going to make those two vectors point in the same direction, right? It doesn't do anything about where they're located, but it says they're going to point in the same direction, right? But we had those point-to-point constraints that say, okay, put those points on the same line. So now with the combination of our point-to-point constraint and our unit vector constraints, we now have those two vectors lying exactly on the same line, right? And then we do the same thing for that center axle section for the center and the axle section on the right bird cage, right? And we do that same thing. We make the unit vectors equal, and that forces all those vectors, or all those little axle sections, to point in the same direction, right? And then the point-to-point constraints gets them to all line up, right? And so now we've got these three bodies with these three axle sections that all lie on the same line. So now there's another aspect of all this, though, that I want to point out. So at this point, we've now got our left bird cage that is connected to the chassis via the two 4-bar links and the shock. It's connected to the center axle assembly, and everything is lined up. And then same thing on the right bird cage. It's all connected to the chassis, and all of the axle assemblies are in line. Now, having those axle components connected at a point allows those axle sections to rotate, right? So at this point, we've got our two axle sections in alignment, but we've still allowed a degree of freedom to allow the one axle section to move, right? And so that's how we allow that bird cage to rotate around the axle, is we have allowed that entire body to rotate around that point that it connects to the center axle connection, right? Does that make sense? And then it also allows that center axle section to move up and down because it's, or not move, but rotate, because it is going to rotate as with a reaction to the engine torque, right? Because it needs to rotate independently. And then the same thing on the right side, you've got this other birdcage assembly that can now rotate, right? So you've got this axle that is constrained by the 4-bar links on the left, the 4-bar links on the right, the J bar, and then the left rear spring, the right rear spring, and the 5th arm spring. All of those constraints holding this thing in its constrained position, right? And now what we can do with our data acquisition is at every timestamp in our data acquisition, we get a new set of shock Heim to Heim links. We feed those back to our equation. We recalculate a new position, right? The next timestamp, recalculate a new position, so on and so forth. So over time, you could almost think of this thing as having a degree of animation to it, right? Because if you recalculate a new position for every timestamp point, you now have a clear definition of what your rear end is doing, right? And so that is how all of these constraint equations work together to give us that final solution of what our axle position is, what our birdcage position is, because we know all of those points in 3D space, but now not in the local coordinate system, but we know what they are in the chassis coordinate system. And we can, again, change our shock Heim to Heim points randomly and recalculate what the new chassis coordinate system points are for every one of those points. And so that is what gives us that position definition of our rear axle assembly, right? Okay. And so these are the 47 equations that define our model, right? So our 47 equations to solve for our 47 unknowns. And that is the mathematical model that defines that rear suspension for our dirt late model. All right, so our live axle decoupled rear suspension, this is the mathematical model that will define that system. And so here's where we have returned our FEQs, our equations. So we're returning the results of our equation, or returning the equations, I guess I should say. And then down here is where we are using the least squares model to pass our arguments and our functions and our initial guesses. And we this is where we get the results for those unknowns to populate that X array. And so then we return that value back to our original call to that function, and that is where we can get the results. And so that is where that is how we do that calculation. And so we ultimately end up with data points, 3, an X, a Y, and a Z for all of those unknown points. Okay, so now that we've got our mathematical model built and we've kind of walked through some of the code and the calculations, let's go put it to the test and let's see what the model outputs are compared to the Autodesk Inventor model. So if we come over here and look at this model, we can see that I currently have all of the links set, and I have the 5th arm shock at 17, the left rear shock at 17, and the right rear shock at 18. So if we look over here in our model, I've got all those values set. I've got the left rear set at 17, the 5th arm at 17, and the right rear at 18. So if I run that here, all right, so if we look at point 2, which is the left side, rear left side, and we come down here, let's Let's look at our upper bird cage, which would be 0.2. So I've got minus 53.426. Right here, minus 53.426 for the X, 23.531 for the Y, and 24.122 for the Z, right? So upper bird cage looks good. Let's go pick a different value. Let's look at the outer hub. So my outer hub here is I think I got those labeled wrong. That should be 21, not 22. It is minus 52.836, 31.966, and 19.540, right? So everything on the left bird cage looks good. Why don't we go pick some values on the center axle, and we'll see what we get there. So let's look at the lower bird cage, or lower J bar, which would be 0.9. So minus 44.289, minus 0.117, and 12.627. That looks good. Let's go look at the lower fifth arm. Let's see, which would be 0.11, I believe. So minus 14.205, minus 577, 14.134. So everything on the fifth arm looks good. Let's just pick up a couple points on the right side just to be complete here. Let's see. Let's try the lower four bar. Let's see, which would be 0.16. So I got minus 52.119, minus 20.216, 15.840, right? So I don't know, let's try maybe the lower spring here, which would be 18. So minus 46.833, minus 19.730, and let's see, 14.016, right? So everything there looks the same. All right, so let's try changing a couple of those spring values. Let's say the left rear goes to 18. Let's put the fifth arm at 16 and put the right rear at 17. All right, so what did I say there? Left rear at 18. Fifth arm at 16. And the right rear at 17. Okay. So let's go look at those and see again where we're at. So let's try the upper for 4-bar link. Minus 53.037, 24.087, 22.704, right? So those are all the same. Let's try the, I don't know, lower shock. Which would be 0.3 minus, or 0.6, minus 56.546. 21.795 and 10.9923. Yep. Let's just do a couple points on the right side, see what they say. Try the lower shock, which would be 18, minus 46.568, minus 46.568, minus 19.653, and 15.101. All right, so there you have it. We are well within a thousandths of an inch matching what Autodesk Inventor says. So that's not too bad. Again, this is all code that we just wrote on our own, right? So, and it works. So again, this is hopefully helps you. I hope you find some value in this. This would be a really good way to utilize that data acquisition, or if you maybe don't have access to a solid model program, it probably would be foolish to do this if you have good access to SolidWorks or Inventor and you are savvy with that stuff. Maybe there's better ways of doing this, but if you don't, this is a good cheap alternative that you can do on your own. I know it's really easy to tie Python code in with other data source systems, so however your data acquisition kicks data out, Python's probably going to be pretty easy to integrate with it. So there may be value in having a system like this. The other thing is, now that you've got the rear suspension, now you can add this to the front suspension stuff that we've already built, and now you've got basically a full vehicle model of your race car suspension, right? And so you could imagine if you had data acquisition on your steering rack, both your front shocks and your 3 rear shocks, I mean, you know exactly what your car is doing, right? And so that is really the value in doing this kind of thing, And anyway, there you have it. Like I said, I hope this helps you. Even if you don't use it, I hope you learned something. And if you got value, again, please help me out. Subscribe, like, all that good stuff. If you ever see me at the racetrack, stop, say hi. Hang out at Lucas Oil Speedway quite a bit, usually, or I-70 in Missouri. Any Missouri tracks, I'll probably be around. So stop me if you say hi, or if you see me, say hi. And again, hope you enjoyed it. All right. Until the next one. Okay. Thank you.